Good day, students. Today we start a course in physics. My name is Yeliseyeva Svetlana Vyacheslavna. I'm your lecturer. The course consists of lectures and laboratory works. There will be 9 lectures in medical physics in total. And there will be 6 laboratory works in laboratory practice. In physics, the experiment occupies the main place, so we will carry out laboratory works. And it's very good if you do it offline. And not so good if you do it online. But the important information for you. Each group is divided into subgroups A and B. And each subgroups has its own teacher. Look at the table, please. Look at the table and find your group number. And your goal, look at the table and remember your teacher for laboratory practice. If you do laboratory practice online, you have to remember your teacher, and you should submit your reports and answers to test question only to your teacher. Because only he or she will give you a credit in physics in summer. To get credit, you need complete laboratory reports online, write answer to test question in writing form, take photo and submit your report and your answers only to your teacher. If you do this simple instruction, I think will be okay. And now, your homework after this lecture, your homework. You have to read a lecture, read a PDF file. I attached it, and for offline student, prepare for laboratory practice a sheet of paper, A4 format, and pen, pencil, ruler, and eraser, and a graph paper. Prepare a graph paper and print, download a print a title page. Title page I attached in the lecture. And you have to take a short test. I will open the test today or tomorrow for you. And that's all. And your homework. Read the lecture. Prepare a sheet of papers for laboratory practice. Print a title page. Prepare a graph paper and pen, pencil, ruler, and eraser. And take a short test after lecture. I will open this test for you today or tomorrow. That's all. And now lecture. And look at my presentation, please. Now we talk about basics of kinematics and dynamics. And look the picture and the branches, and talk about the branches of mechanics. Mechanics is a branch of physics describing physical properties of bodies and rules of their mechanic motion. Mechanics is concerned with the motion of bodies under the action of forces, including the special case in which a body remains at rest. Our first concern in the problem of motion are the forces that bodies exert on one another. This leads to the study of such topics as gravitation, electricity, and magnetism according to the nature of the forces involved. Given the forces, one can seek the manner in which body moves under the action of forces. This is the subject matter of mechanics proper. Mechanics is basically divided into two parts, statics and dynamics. Dynamics is further divided in kinematics and kinetics. Statics, it deals with the study of behavior of body at rest under the action of various forces that are in equilibrium. Dynamics is study of object in motion. And kinematics, it deals with the motion of body without considering the forces acting on it. And kinematics as a field of study is often referred to as geometry of motion, and is occasionally seen as a branch of mathematics. A kinematics problem begins by describing the geometry of the system and declaring the initial condition of any known values of position, velocity, and or acceleration of points within the system. Then, using arguments from geometry, the position, velocity, and acceleration of any unknown parts of the system can be determined. And we consider two types of motion. And first of all, translational motion. And the second, rotational motion. And the first, translational motion is the motion by which a body shifts from one point in space to another. One example of translational motion is the motion of a bullet fired from a gun. An object has a rectilinear motion when it moves along a straight line or straight direction. Rotational motion deals only with rigid bodies. A rigid body is an object that retains its overall shape, meaning that the particles that make up the rigid body remains in the same position relative to one another. A wheel and a rotor motor are common examples of rigid bodies that commonly appear in questions involved rotational motion. Angular motion is a common type of rotational motion. Translational motion, defined in kinematics. Kinematics is the study of the motion of point, object, and group of objects without considering the cases of its motion. Kinematics is a branch of classical mechanics that describe the motion of point, object, and the system of group of objects without reference to the cases of motion or forces. The study of kinematics is often referred to as the geometry of motion. Objects are in motion all around us. Everything from a tennis match to a space probe flyby of the planet Neptune involves motion. When you are resting, your heart moves blood through your veins. Even in inanimate object, there is a continuous motion in the vibration of atoms and molecules. Interesting question about motion can arise. How long will it take for a space probe to travel to Mars? Where will a football land it thrown at a certain angle? And an understanding of motion, however, is also key to understanding other concepts of physics. And understanding of acceleration, for example, is crucial to the study of force. To describe a motion, kinematics studies the trajectories of point, line, and other geometric objects, as well as the differential properties. Kinematics is used in astrophysics to describe the motion of celestial bodies and systems, and in mechanical engineering, robotics, and biomechanics to describe the motion of systems composed of joint parts. A formal study of physics begins with kinematics. The word kinematics comes from a Greek word kinesis, meaning motion, and it's related to other English words such as cinema, movies, and kinesiology, the study of human motion. Kinematics analysis is the process of measuring and the kinematics quantities used to describe motion. The study of kinematics can be abstracted into purely mathematical expressions, which can be used to calculate various aspects of motion, such as velocity, acceleration, displacement, time, and trajectory. Displacement. Is the change in position of an object relative to its reference frame. For example, if a car moves from a house to a grocery store, its displacement is the relative distance of the grocery store to the reference frame or the house. The word displacement implies that an object has moved or has been displaced. Displacement is a change in position of an object and can be represented mathematically as follows. Look here. Where delta x is a displacement, xf is a final position, and x0 is the initial position. A vector is any quantity what has both magnitude and direction, whereas a scalar has only magnitude. What is the difference between distance and displacement? Look at the picture. Whereas displacement is defined by both direction and magnitude, distance is defined by magnitude alone. Displacement, an example of vector quantity. Distance is an example of scalar quantity. In mathematics, physics, and engineering, a vector is a geometry object that has a magnitude and direction and can be added to other vectors according to vector algebra. The direction of a vector in one-dimensional motion is given simple by a plus or minus sign. In everyday usage, the terms speed and velocity are used interchangeably. In physics, however, they are distinct quantities. Speed is a scalar quantity and has only magnitude. Velocity, on the other hand, is a vector quantity and so has both magnitude and direction. This distinction becomes more apparent when we calculate average speed and velocity. Average speed is calculated as the distance traveled over the total time of travel. In contrast, average velocity is defined as the change in position or displacement over the total time of travel. Average velocity is displacement divided by the time of travel, where V indicated by the bar over the V, it's indicated average. V with a bar, it's a velocity. Delta x is the change in position or displacement, and xf it's a final, and x0 it's initial position at time tf and t0 respectively. If the starting time t0 is taken to be 0, then the average velocity is simply write down these forms. It's delta x divided by t. The c unit for velocity is meters per second. And instantaneous velocity is the velocity of an object at a single point in time and space is calculated by the slope of the tangent line. Typically, motion is not reach constant velocity, no speed. While driving in a car, for example, we continuously speed up and slow down. A graphical representation of our motion in terms of distance versus time, therefore, would be more variable or curvy rather than a straight line, indicating motion with a constant velocity as shown below. To calculate the speed of an object from a graph representing a constant velocity, all that is needed is to find the slope of the line. This would indicate the change in distance over the change in time. However, change in velocity, it is not as straightforward. Since our velocity is constantly changing, we can estimate velocity in a different ways. One way is to look at our instantaneous velocity represented by one point on our curvy line of motion graphed by distance versus time. In order to determine our velocity at any given moment, we must determine the slope at the point. To do this, we find a line that represents our velocity in that moment shown graphically in. That line would be the line tangent to the curve at that point. If we extend this line, we can easily calculate the displacement of a distance over time and determine our velocity at that given point. The velocity of an object at any given moment is the slope of the tangent line through the relevant point in its x versus t graph. Determine instantaneous velocity. The velocity at any given moment is denoted as the slope of tangent line through the relevant point of the graph. Instantaneous speed equals to the magnitude of the instantaneous velocity. And then when a particle's velocity change, the particle is set to undergo acceleration. For motion along an axis, the average acceleration over a time interval delta t is delta v divided by delta t, where the particle has velocity v first at the time t first, and then velocity v second at the time t second. The instantaneous acceleration is a equal dv by dt. Acceleration has both magnitude and direction. Its algebraic sign represented its direction on an axis, just as for displacement and velocity. That is, acceleration with a positive value is in the positive direction of an axis, and acceleration with a negative value is in the negative direction. If you tossed an object either up or down and could somehow eliminate the effects of air and its flight, you would find that the object accelerates downward at a certain constant rate. That rate is called the free fall acceleration, and its magnitude is represented by g. Looked here, free fall acceleration. The acceleration is independent of the object's characteristics such as mass, density, or shape. It is the same for all objects. An important example of straight line motion with a constant acceleration is that of an object rising or falling freely near Earth's surface. The constant acceleration equations describe this motion, but we make two changes in notation. We refer the motion to the vertical y-axis with a plus y vertically up. And we replace a with g, where minus g is the magnitude of the free fall acceleration. Near Earth surfaces, g equal 9.8 meter per second square. Looked here. And when you divide the acceleration vector into its components relative to plane curves, you express it in terms of the acceleration tangent to the curves and the acceleration normal or perpendicular to the curve. Look at the picture. This component tangent and the normal. This point of trajectory. And some expression for a normal component and for tangent or component. And for acceleration. It's a model. In many types of motion, the acceleration is either constant or approximately so. For example, you might accelerate a car at an approximately constant rate when a traffic light turns from red to green. Later, when you brake the car to a stop, the acceleration might also be approximately constant. Such cases are so common that a special set of equations has been derived for dealing with them. These equations are valid only for constant acceleration. And look at the picture. There are kinematic equations that relate displacement, initial velocity, final velocity, acceleration, and the time. And there are five expressions to describe a kinematic motion. And in different problems, we have a missing acceleration or initial velocity or final velocity, maybe displacement or time, and our goal to find other values, and we can use these five expressions. And look, the first and this formula is missing acceleration, but this formula is missing initial velocity, but this is missing final velocity. This formula is missing displacement, and this formula is missing time. And then angular motion. Angular position in the mathematics, the angle of rotation is a measurement of the amount that a figure is rotated about a fixed point, which we take as the zero angular position. From geometry, we know that theta is the angle. It's given by this S. This theta is equal S, this display divided by R, is a radius. And S, it is an arc. S is a length of circular arc that extend from the x-axis to the reference line, and R is a radius of the circle. Changing the angular position of the reference line from theta first to theta second, the body undergoes an angular displacement, delta theta, given by delta theta, look at here, is a final minus initial position. And delta t, this final time and initial time. This definition of angular displacement holds not only for the rigid body as a whole, but also for every particles within that body. If a body is in translational motion along an x-axis, its displacement delta x is either positive or negative, depending on whether the body is moving in the positive or negative direction of axis. Similarly, the angular displacement delta theta of a rotating body is either positive or negative according to the follow rule. An angular displacement in the counterclockwise direction is a positive, and one in the clockwise direction is negative. The phrase clocks are negative can help you remember this rule. They certainly are negative when their alarm sounds off early in the morning. And angular velocity. Angular velocity, looked here, it's omega. Suppose that our rotating body is at angular positive theta first and at time t first, and at angular position theta second and the time second. We defined the average angular velocity of the body in the time interval delta t from t first to t second. And different of angles to different of time, where delta theta is the angle displacement during delta t. The instantaneous angular velocity with which we shall be most concerned is the limit of the inertia as delta t approaches zero. If we know theta, we can find the angular velocity by differential. The magnitude of an angular velocity is called the angular speed, which is also represented with omega. Angular acceleration. And the angular acceleration, it's epsilon. If the angular velocity of a rotating body is not constant, then the body has an angular acceleration. Let omega 2 and omega first be its angular velocities is a time 2 second and t second and t first respectively. The average angular acceleration of the rotating body in the interval from t first to t second is defined as here, or not second and the first, it's a final and initial. It's delta omega is a change in the angular velocity that occurs during the time interval delta t. The instantaneous angular acceleration with which we shall be most concerned is the limit of this quantity as delta t approaches 0. The unit of angular acceleration is commonly the radian per second squared. Angular quantities are vectors. It's very important, be attentive. We can describe the position, velocity, and acceleration of a single particle by means of vectors. If the particle is confined to a straight line, however, we do not really need vector notation. Such a particle has only two directions available to it, and we can indicate these directions with plus and minus signs. In the same way, a rigid body rotating about a fixed axis can rotate only clockwise or counterclockwise as seen along the axis. And again, we can select between the two directions by means of plus and minus signs. The questions arises, can we treat the angular displacement, velocity, and acceleration of an rotating body as vectors? The answer is qualified yes. Consider the angular velocity. We can represent angular velocity as a vector pointing along the axis of rotation. Look here. How detection of direction of angular velocity? It's a right hand, and your finger direct of rotation, where is a V? It's a direction of V. And then we find a direction of angular velocity. Then we establish a direction for the vector v by using a right-hand rule. Curl your right hand about the rotating record, your fingers pointing in the direction of rotation. Your extended thumb will then point in the direction of the angular velocity vector. Remember it. If the record were to rotate in the opposite sense, the right-hand rule would tell you that the angular velocity vector then points in the opposite direction. Now, for the quotient, angular displacement cannot be treated as vectors. Why not? We can certainly give them both magnitude and direction, as we did for the angular velocity vector. However, to be represented as a vector, a quantity must also obey the rules of vector addition. One of which says that if you add two vectors, The order in which you add them do not matter. Angular displacement fail this test. Relating the linear and angular variables. Rotation with a constant angular acceleration. In pure translation motion with a constant linear acceleration is an important special case. In pure rotation, the case of constant angular acceleration is also important, and a parallel set of equations holds for this case also. We shall not derive them here, but simply write them from the corresponding linear equation, substituting equivalent angular quantities for the linear ones. And look at these tables. When a rigid body such as a merry-go-round rotates around an axis, which particles in the body moves in its own circle around that axis, since the body is rigid, all the particles make one revolution in the same amount of time. That is, they all have the same angular speed omega. However, the further a particle is from the axis, the greater than circumference of its circle is, and so the faster its linear speed v must be. You can notice this on a merry-go-round. You turn with the same angular speed omega regardless of your distance from the center, but your linear speed v increases noticeably if you move to the outside edge and the merry-go-round. We often need to relate the linear variables s, v, and a. It's displacement, velocity, and acceleration, particular points in a rotating body to the angular variables. Theta is angle, omega, it's angular speed, angular velocity, and epsilon, angular acceleration for that body. The two sets of variables are relative by r, the perpendicular distance of the point from the rotational axis. This perpendicular distance is the distance between the point and the rotational axis, measurement perpendicular to the axis. It's also the radius of the circle traveled by the point around the axis of rotation. Look at these tables. This equivalent of angular quantities to the linear, and linear velocity to angular velocity, but the time not change, and acceleration to angular acceleration, and these initial values. And look at this equation of kinematics. These formulas for translational motion, it's a linear equation, and this express a rotational motion, these angular equations. And the dynamics and Newton's laws. We have seen that part of physics is a study of motion, including acceleration, which are change in velocities. Physics is also a study of what can cause an object to accelerate. That cause is a force, which is, loosely speaking, a push or pull on the object. The force is set to act on the object to change its velocity. When a car slams into a telephone pole, or force on the car from the pole causes the car to stop. Since engineering, legal, and medical journals are filled with articles about forces and objects, including people. Newtonian mechanics the study of that relation as Newtonian represented it is called Newtonian mechanics. We shall focus on its three primary laws of motion. Newtonian mechanics does not apply to all situations. If the speeds of the interaction bodies are very large, and appreciable fraction of the speed of light, we must replace Newtonian mechanics with Einstein's special theory of relativity, which holds at any speed, including those near the speed of light. If the interesting bodies are on the scale of atomic structure, we must replace Newtonian mechanics with quantum mechanics. Physicists now view Newtonian mechanics as a special case of these two more comprehensive theories. Still, it's a very important special case because it applies to the motion of object ranging in the size from the very small to astronomical. Newton's first law. Before Newton formulated his mechanics, it was through that some influence, a force, was needed to keep a body moving at a constant velocity. Similarly, a body was thought to be in its natural state when it was at rest. For a body to move that constant velocity, it seemingly had to be propelled in some way by a push or a pull. Otherwise, it would naturally stop moving. These ideas were reasonable if you send a pig sliding across a wooden floor. It does indeed slow and then stop. If you want to make it move across the floor with a constant velocity, you have to continuously pull or push it. Send and park sliding over the ice of a skating rink, however, and it goes a lot farther. You can imagine longer and more slippery surfaces over which the park would slide farther and farther. In the limit, you can think of a long, extremely slippery surface over which the park would hardly slow. From this observation, we can conclude that a body will keep moving with a constant velocity if no force acts on it. That leads us to the first of Newton's three laws of motion. Newton's first law: if no force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. In other words, if the body is at rest, it stays at rest. If it is moving, it continues to move with the same velocity. Force. We now wish to define the unit of force. We know that a force can cause the acceleration of body. Thus, we shall define the unit of force in terms of the acceleration that a force gives to a standard reference body, which we take to be the standard kilogram. This body has been assigned exactly and by definition a mass of 1 kilogram. We put the standard body of a horizontal frictionless table and pull the body to the right, so that by trial and error it eventually experiences a measured acceleration of 1 meters per second square. We then declare as a matter of definition that the force we are exerting on the standard body has a magnitude 1 Newton. It's an abbreviation N. Then forces are most often represented with a vector symbol such as F. Just a moment. F with a vector, and a net force is represented with a vector symbol F net. As will other vectors, or if as with other vectors, a force or a net force can have component along a coordinate axis. When forces act only along a single axis, they are single component forces. Then we can drop the overhead arrows and the force symbols and just use sign to indicate the directions of the force along that axis. Instead of the wording used above, the more proper statement of Newton's first law is the term of net force. Newton's first law. If no net force acts on a body, if the net force is equal 0, the body's velocity cannot change, that is, the body cannot accelerate. And then Newton's second law. All the definitions, experiments, and observations we have discussed so far can be summarized in one net statement. Newton's second law. The net force on a body is equal to the product of the body's mass and its acceleration. It's F net. Look at this expression equal to m and a. It's a mass and acceleration. This equation is simple, but we must use it cautiously. First, we must be certain about which body we are applying it to. Then force net must be the vector sum of all the forces that act on that body. Only forces that act on that body are to be included in the vector sum, not forces acting on other bodies that might be involved in the given situation. Every time you work a force problem, you firstly step is to clearly state the body to which you are applying Newton's law. This expression tell us that if the net force on a body is 0, the body's acceleration equals 0. If the body is at rest, it stays at rest. If it is moving, it continues to move at a constant velocity. In such cases, any forces on the body balance on another, and both the forces and the body are said to be in equilibrium. Commonly, the forces are also said to cancel one another, but the term cancel is tricky. It does not mean that the forces case to exit. The forces still act on the body. For C units tell us that 1 Newton is 1 kilogram multiplied by 1 meters per second in square. To solve problem with the Newton's second law, we often draw a free body diagram in which the only body shown is one for which we are summing forces. A sketch of the body itself is preferred by some teachers, but to save space in this we shall usually represent the body with a dot. Also, each force on the body is drawn as a vector, a row with its tail in the body. A coordinate system is usually included, and the acceleration of the body is sometimes shown with a vector arrow. And some particular forces. And first of all, the gravitational force. A gravitational force on a body is a certain type of pull that is directed toward a second body. Above, we do not discuss the nature of this force and usually consider situation in which the second body is Earth. Thus, when we speak of the gravitational force on a body, we usually mean a force that pulls in it directly toward to the center of Earth. That is directly down toward the ground. We shall assume that the ground is an inertial frame. Suppose a body of mass m is in free fall with a free fall acceleration of magnitude g. Then if we neglect the effects of air, the only force acting on the body is the gravitational force. We can relate this downward force and downward acceleration with Newtonian second law. We place a vertical y-axis along the body's path with the positive direction upward. For this axis, Newton's second law can be written in the form minus Fg is equal m to product minus g. Or in a question form, it's Fg equal product m and g, and free fall acceleration. In words, the magnitude of the gravitational force is equal to the product m and g. It's free fall acceleration. And then weight, the weight P, weight, P of a body is the magnitude of the net force required to prevent the body from falling freely as measured by someone on the ground. Now, let us generalize the situation. Consider a body that has an acceleration of 0 relative to the ground, which we again assume to be an inertial frame. Two forces act on the body, a downward gravitational force and a balancing upward force of magnitude P. The weight P of a body is equal to the magnitude Fg. Look at here. Of the gravitational force on the body. And P is equal to M, product M and G. Then the normal force. If you stand on a mattress, earth pulls you downward, but you remain stationary. The reason is that the mattress, because it deforms downward due to you, pushes up on you. Similarly, if you stand on a floor, it deforms and pushed up on you. Even a seemingly rigid concrete floor does this. The push on you from the mattress or floor is a normal force. The name comes from the mathematical term normal, meaning perpendicular. The force on you from, say, the floor is perpendicular to the floor. When a body presses against a surface, the surface deforms and pushes on the body with a normal force that is perpendicular to the surface. Then the magnitude of the normal force is Fn equal to sum mg and ma, or product mg plus ay. For any vertical acceleration ay at the table and the block, if the table and block are not accelerating relative to the ground, then ay is equal 0 and Fn equal only product m and g. And friction. If we as a slide attempt to slide a body over a surface, the motion is resisted by a bonding between the body and the surface. The resistance is considered to be a single force, called as the frictional force or simply friction. This force is directed along the surface opposite the direction of the intended motion. Sometimes, to simplify a situation, friction is assumed to be negligible. Tension. When a cord is attached to a body and pulled taut, the cord pulls on the body with a force directed away from the body and along the cord. The force is often called a tension force because the cord is said to be in a state of tension. Which means that it is being pulled taut. The tension in the cord is the magnitude T of the force on the body. Tension, so T. And Newton's third law. When two bodies interact, the forces on their bodies from each other are always equal in magnitude and opposite in direction. And then energy. The term energy is so broad that a clear definition is difficult to write. Technically, energy is a scalar quantity associated with the state of one or more object. Kinetic energy is energy associated with the state of motion of an object. The faster the object moves, the greater its kinetic energy. When the object is stationary, its kinetic energy is zero. For an object of mass m, whose speed v is well below the speed of light. And kinetic energy is equal half of product m and v in square. The C unit of kinetic energy is a joule. Work A, magnitude A, is energy transferred to or from an object via a force acting on the object. Energy transferred to the object is positive work, and from the object negative work. Work and kinetic energy. For a particle, a change kinetic energy in the kinetic energy equals the net work A done on the particle. And conservation of energy. The total energy of a system, this is the sum of its mechanical energy and its internal energies, including thermal energy, can change only by amounts of energy that are transferred to or from the system. This experimental fact is known as the law of conservation of energy. And moment of inertia. The kinetic energy of a rigid body rotating about a fixed axis is given by this equation, where I is a rotational inertia of moment of inertia of the body, and I defined by as a sum of product particle mass and r in square. R is a distance from an axis. And then, very important, the parallel axis theorem. The parallel axis theorem relates the rotational inertia of a body about any axis to that of the body, of the same body, about a parallel axis through the center of mass. Here, A is a perpendicular distance between two axes, and x I cm is the rotational inertia of the body about the axis through the center of mass. Look at these tables. These examples of some body and calculation of its rotational inertia. It's a moment of inertia. And then a moment of force or torque. Torque is a turning or twisting action on a body about a rotational axis due to a force. If force is exerted at a point given by the position vector r relative to the axis, when the magnitude of torque is, look at here, but this m is a moment of force or torque. It's a vector product, and when we write down a vector product, we can see theta. It's an angle between a force and a radius vector, and d. It's a d. Is a moment arm, and d is equal r sin theta. And Newton's second law in angular form, we can see, is a moment of force or torque. This net force, it's a sum of different forces, equal to a moment of inertia product with angular acceleration. Is Newton's second law in angular form. And work and rotational kinetic energy. Work is the product of torque and different of angle, and rotational kinetic energy is half of product is the moment of inertia and angular velocity in square. And different of this kinetic energy is a work. Angular moment. In physics, angular moment is the rotational equivalent of linear momentum. It is an important quantity in physics because it is a conserved quantity. The total angular momentum of a closed system remains constant. This is a conservation law, and L is a constant. And look at this picture. But now we know about direction of angular velocity. And look at this expression, and now we know direction of angular momentum. Because angular momentum is a vector product, and its direction defined by a vector product. And some example, the spin volunteer. The spinning volunteer. Suppose that the initially rigid body somehow redistributes its mass relative to that relation axis, changing its rotational inertia about that axis. We write this conservation law as product of moment of inertia and angular velocity initial, or the first case, is equal to product moment of inertia and angular velocity. It's a final, or other cases. Here the subscripts refer to the values of the rotational inertia and angular speed before and after the redistribution of mass. Picture A show a student seated on a stool that can rotate freely about a vertical axis. The student who has been set into rotational at a modest initial angular speed holds two dumbbells in his outstretched hands. His angular moment vector L. Look at here. It's a L and the initial angular velocity. L lies along the vertical rotational axis, pointing upward. The instructor asked the student to pull in his arms. This action reduces his rotational inertia from its initial values to a smaller value IF, because the moves mass closer to the rotational axis. His rate of rotational increases marked from VI to VF. The student can then slow down by extending his arms one more, moving two dumbbells outward. No net external torque acts on the system consisting of the student's stool and dumbbell. With the angular moment of that system about the rotational axis must remain constant no matter how the student maneuvers the dumbbells. The student's angular speed, omega initial, is relatively low, and his rotational inertia, I initial, is relatively high. According to some expression, his angular speed must be greater to compensate for the increased IF. Under this IF, but is a small velocity and it's a big velocity, angular velocity, and angular velocity and angular acceleration. But now that's all. I thank you for your attention. Your homework, please. Your homework, read this lecture. I attached this file. Prepare to laboratory practice. It's prepare a sheet of paper, a graph paper, a pencil, pen, ruler and eraser, and print a title page. It's a title page. And after this lecture, I will open for you a test today or tomorrow. I open for you a test, and you have to take a test after this lecture. And that's all. Thank you for your attention. Read the lecture and see you later. See you next lecture. Goodbye.